Hi, everyone. I'm Kathy Demchak from Penn State, and I'd like to welcome you to this session where we'll hear two forward-looking talks that discuss the future in pest and disease management. Our two speakers for this session are Inga Zasada and Fumi Takeda. Inga will be speaking on what is the future of nematode management in caneberries, and Fumi will discuss managing diseases and pests with UVC light. Inga is a research plant pathologist with the USDA Agricultural Research Service Horticultural Crops Research Laboratory in Corvallis, Oregon. Her research program focuses on the management of plant parasitic nematodes in small fruits and other horticultural crops. Fumi is a senior research scientist working for the USDA Agricultural Research Service at its Appalachian, depending on where you're from, Fruit Research Station in Kearneysville, West Virginia. Fumi has worked on many different plant physiology and production-related projects over the years, including ones related to trellis design and mechanical harvesting. I'd like to thank Naturite Farms, our host sponsor for this afternoon's session. We very much appreciate their support as it helps greatly in defraying the costs of putting on a conference like this one, and it helps with keeping our registration fees low. We encourage you to learn more about Naturite Farms by visiting the link to their company information on the conference website. During these talks, feel free to type any questions into the Q&A pod, which you should be able to access by clicking the Q&A icon at the top or bottom of your screen. Please specify who your question is for. We will answer as many of these as possible, either live or as a typed response. So with that, we will move on to our talks.
All right. Hi, good afternoon. Thank you for the invitation to present today on my knowledge of nematodes and what I think about nematodes and caneberries and some ideas for the future and how we might manage them. My contact information is here, my email as well as the website for my lab if you want to find any further information. Quick presentation outline for the next 20 or so minutes. First, I'll talk about the problem of nematodes in caneberry production, talk about the current management options that caneberry growers have, and then some ideas for the future on how we might want to direct resources and efforts to help solve this problem. Just some images here of caneberry production in the Pacific Northwest, up in northern Washington, as well as in California. This upper image right up here is of a field being full field fumigation in California. So what's the problem? It's nematodes. You probably don't think about it with a warm heart, but I do since I work with them every day. This word cloud kind of shows the genera of nematodes that have been reported in caneberries. It's not a long list, probably 5 to 6 genera, a total of 10 or 15 species, of which 2 are the most important, and they're in the larger words here in this word cloud, and that's Pratylenchus and Xiphinema. So just a little bit more about these 2 important nematode parasites of caneberries that I'll be focusing on today during my talk. First of all, Pratylenchus penetrans is the root lesion nematode. It's a migratory endoparasite. So what it will do to caneberry plants is that it will migrate around in soil, it will invade the roots, and essentially it's not a very, it doesn't have a very close association with the host like some other nematodes. Rather, it just goes through cells, pierces with its feeding part in the upper part of the nematode head that you can see here. It will take out what it needs from the plant and it will essentially destroy cells in the root, and hence the name root lesion on roots other than caneberry roots, which tend to be pretty dark. And you will be able to see the necrosis of root cells as the nematode feeds. The second nematode that I'll talk a little bit about, not a tremendous amount because we don't have it widespread here in the Pacific Northwest up in northern Washington, is a dagger nematode, Xiphinema americanum. This nematode is certainly most impactful probably on the East Coast where it's thought to be native. It's a migratory ectoparasite as compared to the root lesion nematode. It uses a similar type of structure in the front end of the nematode to pierce roots and to get its nutrients. By itself, it's probably not a huge detriment to the production of raspberries or caneberries, but it does vector viruses, which can be very devastating, and that includes things such as tomato and tobacco ring spot virus. So what we really care about is the economic impact that these nematodes cause to caneberries. And here's just some of the information that we currently have. On the left-hand side, we'll start with root lesion nematodes, some of the work that we've done up in Skagit and Whatcom counties in Washington State. On the left-hand side, we had a multi-year trial where we grew a diversity of raspberry genotypes in soil either fumigated with 1,3-dichloropropene or not. And then we monitored growth over the years. And you can see there was a tremendous consequence of nematode parasitism on meeker, which is shown here. So the top image is the growth that you would see of meeker in a non-fumigated, in a fumigated plot and one in not. And you can use this drip line as a reference point to just demonstrate how reduced the growth of meeker was in this situation. In a second trial that we conducted in Whatcom County, similarly, we either fumigated or not fumigated areas, again with 1,3-dichloropropene, planted raspberry. This field didn't have as high of a nematode pressure as this other one. And then 2 years later, looked at a full yield crop, and that's shown here, yield as kilograms per subplot. And again, we saw a significant reduction in yield of plants that were grown in non-fumigated ground, about 10%. And I think this is probably a more realistic reduction in yield by a nematode. You look at the literature, and across nematode species, it's estimated that nematodes cause anywhere from 8 to 10% yield loss annually globally due to nematode parasitism. Back to dagger nematode, that migratory ectoparasite. Again, the nematode by itself, which usually doesn't reach super high populations in caneberries, is probably not a problem. But the problem is when the virus is present and the nematode is able to acquire it and transmit it to plants. And that's shown here in this image where you get this see-through row of raspberries. Not a whole lot of growth here, probably not producing a lot of fruit, but 100% yield reduction when the virus is present. And of course, you're going to start to get spread within this field, which can be devastating. The other devastating part is that it's very hard to remediate this situation once it occurs. So there's the two economic impact of the two major nematode parasites in raspberry. So how we currently manage them. And this image here in the middle is a fumigation rig applying Fumigate in California, and certainly here in the western states, and that being California, where a lot of the fresh market production occurs, and up in Whatcom County, where a lot of the processed production occurs, fumigation is central to the management of nematodes. In California, fumigation happens approximately every 18 months in that production cycle. And up north in Whatcom County, depending upon the length of the planting, which has been shortened over time, you could potentially be fumigating ground every 5 years prior to replanting. So again, a really critical part to the success of the raspberry and caneberry industry in the western states. However, there are other things that can be done to manage nematodes. The great thing about fumigation is as long as it's done in a proper manner, it's very efficacious. Some of these other management practices that I'm showing you outside this circle require a little bit more knowledge about nematodes, a little more diligence on part of a grower. Examples include rotation. Can you go out a raspberry for a while? This would be something that would work for dagger nematode because the nematode loses the virus as it matures. So you could go out a raspberry or caneberries for a while, come back in after the nematode had lost the virus, and that would be successful. For root lesion nematode, maybe not as successful considering it has a very wide host range. Down here, anaerobic soil disinfestation certainly has received quite a bit of attention in California in caneberry and strawberry fields. I know they're seeing efficacy, and this would certainly be an option, although very expensive, but maybe a really good option for organic growers. And I'll just touch on the final one, nematicides. We currently have 2 to 3 new nematicides on the global market that might have a place in controlling nematodes in caneberry fields, and there are trials that are ongoing in several locations. So So that's kind of what we're looking at, not only from caneberry production, but nematode management in most high value commodities kind of follow the same, excuse me, kind of trend. So what's the future? And I kind of was thinking about this, and I kind of decided on two words that I think we need to be thinking about and trying to address research and efforts in to be able to think about nematode management long term. First word is risk, defined as the exposure to the chance of injury or loss. So the question in caneberries is, how do we understand risk, and how do we communicate how risky a situation is for a caneberry grower when they're going into a replant situation? And I'll talk about that a little bit more. The other word that I came up with that I wanted to focus on is resistance. This is the act or power of resisting, opposing, or withstanding. And what I'm arguing here is that if we really want to try to get away from fumigation as the central way that we control nematodes, resistance is going to have to play a big role in this. And I'll show some of the work that we've done and provide some ideas on this for the future. Okay, so let's start with risk. Over here you have your nematodes, and the question is, how risky are they to the production of caneberries in a field? And risk can be influenced in this context by many different variables. The nematode population density, the environment, presence of virus in the case of dagger nematodes, genotype of the plant that you're using, whether it's resistant, which I can tell you right now, there are no resistant caneberry varieties or cultivars to nematodes. But it also could depend on the tolerance of a genotype, whether it's able to be a host for the nematode, but not succumb to the consequences of that nematode. And then there's many more that you could think of. And here we just show a newly planted raspberry field up in northern Washington. So risk, usually when a caneberry grower thinks about risks, it probably has something to do with a nematode report that they might have on their desk, which has reported the number of root lesion nematodes per certain volume of soil. And the question always comes up, well, what does that mean, and what risk does that number pose to me and my ability to produce a economically viable crop? So is one nematode a risk? Are 10 nematodes a risk? Are hundreds of nematodes a risk? And again, I would argue that risk will depend on a lot of different factors, where in some cases 10 nematodes might be of risk to someone in a certain environment, but in another environment, hundreds of nematodes might not be a risk. So those are the kind of things that we need to understand to be able to communicate risk to raspberry and caneberry growers. So I'm going to give you a couple examples from the work that we've done up in Whatcom County of ways we've tried to understand more about nematodes and the risk they pose to the production of raspberries. This study was conducted from 2012 to 14. In this trial, we were really interested in understanding how the use of vidate or oxymil as a post-plant management practice suppressed nematodes during the first couple of years after planting. So we had two different varieties, Wakefield and Meeker. Down here, these colors correspond to our treatments. We either applied vidate twice in June, twice in May, or not at all. And then here along the x-axis are the treatments grouped by sampling date. So we sampled at 6, 12, 18, and 24 months. And this is the mean number of nematodes per gram of root, how we assessed nematode populations. So these are two different fields, similar age. And what I really want to point out here, and I'd really like you to focus in on, is this y-axis here and the numbers that are shown here. So this is what I would consider a very high density field, up to 2,000 nematodes per gram of root. And that's in comparison to this Meeker field, where our maximum densities were 600. And there's very different things going on based upon that initial density of nematode. So in this field where there was high density with vidate applications, you can see that we only protected those plants from nematodes for 6 months. And again, this is in a very high density situation. In this other field where we had lower densities, we were actually able to continue to suppress nematodes 2 years after the initial applications of oxymil. So again, it was applied in the first couple months after planting, and then not again for 2 years. So again, this is risk. In this field, I could say, with a certain amount of confidence to this grower, with the lower population densities that you have, you may be able to suppress nematodes for a longer period of time with this type of application. Whereas in this higher density field, it might be recommended that soil fumigation occur prior to replanting because of the high risk of this field from nematode parasitism. Second example I want to give is where we did some treatments in 2 different fields with 2 different soil types. So a loamy sand field up here and a sandy loam field. Our treatments were, or our time points were pre-fumigation, post-fumigation at planting. Essentially, we went out there, we took deep cores down to 3 feet. We partitioned these into half-foot segments, and that's what's shown here. So this is closer to the soil surface, and this is down to 3 feet down here. And I've circled really what I want to be the take-home message. So treated similarly, these 2 fields that had 2 different soil types. We went in pre-treatment of the blue lines, determined distribution vertically. You can see more nematodes in the top layer of a loamy sand, where nematodes are distributed more deeply in a coarser soil. We then fumigated with metam sodium, and you can see very clearly here that we had a differential response of those nematodes depending on soil type. So with that treatment, we missed some nematodes up in the top, but down below there weren't a lot. And interestingly here, this treatment did a really good job, shallow, but not so good deep. So again, I think we can tailor our knowledge of risk and how we extend information to growers based upon soil type and the need to either be able to control nematodes deep, as in a sandy loam, or maybe not so much in a loamy sand. Okay, I'm going to switch to my other word that I threw out earlier, and that's resistance. And the goal is resistance to the root lesion nematode, what I consider to be the #1 nematode parasite in caneberries. And this is certainly an endeavor that's being pursued in other commodities that struggle with managing this nematode. Currently, there are some genotypes available in walnut that look like they're non-hosts for the root lesion nematode. A lot of work has gone on in alfalfa to look for resistance to root lesion nematode. A different species in grape, but there are resistant rootstocks to root lesion nematodes. And then potato and rose were other 2 examples that I could find where they're pursuing resistance. So the question for us as a group is whether we can achieve something like this in caneberries. Can we identify resistant genotypes, be able to cross those into cultivars that are desirable to folks to plant? So we've done some evaluation of rubus species material. This was done with Pat Moore at WSU before he retired. Pat had a bunch of rubus material available. He tissue propagated that, got it to us, and then we did screenings in greenhouses to look at the host statuses of this material to root lesion nematode. Here we have the species, number of root lesion nematode per pot, and then this RF value is essentially a ratio of final population divided by initial population. So a lower value means that it's a poorer host, and a higher value means that it's a better host. So the best host in this trial was this rubus innomatus, excuse me if I pronounce that incorrectly. Anything below 1 means that it's probably a poor host. Meeker was just a maintenance host, and then you can see we came up with 2 species that appeared to be very poor hosts for root lesion nematode, Rubus leucodermis and Rubus niveus. So we were interested in taking this a little bit further and taking out to the field. This was in that big trial I mentioned earlier where we planted different genotypes into areas that either were fumigated or not. And we included Rubus niveus in this trial. And here's our pictures again. Look at the drip line in both pictures to kind of orient yourself at the amount of growth that occurred. And you can see, unfortunately, in this trial, Rubus niveus was a very good host for the nematode, thousands of nematodes per gram of root, which was counter to what we saw in our greenhouse study. But in spite of heavy nematode pressure, this plant was still able to grow. And so this is what we call tolerance. And I think this is another worthy endeavor to pursue in caneberry germplasm, is whether we can find something that's not necessarily resistant to the nematode, but something that is able to endure continued subjection to something. So it's able to endure that nematodes are always feeding on it and still produce biomass and ultimately, in our case, fruit. So Rubus niveus appears to be something that would be able to achieve that goal. That's in comparison to Willamette, which was also included in this trial. In this case, on the right-hand side is a non-fumigated, on the left-hand side, excuse me, on the right-hand side is a fumigated, on the left-hand side is a non-fumigated. You can see very poor growth of raspberry Willamette when grown in areas with heavy nematode pressure versus plants that were protected from nematodes. So again, this would be considered very intolerant to nematodes. So those are the two kind of main ideas I wanted to get across in my talk. In conclusion, I firmly believe if we want to manage nematodes without soil fumigation, we will need plant resistance. And maybe we're at a point where we have advanced breeding lines that have really good fruit quality, harvestability, and then now we can start to consider not only nematodes but other soil-borne pathogens such as Phytophthora root rot and verticillium. That might be of interest to bringing into the background of those advanced selections. I would also argue that knowledge of factors that influence nematode densities and management efficacy are needed. I think with a little bit more work, we can probably tailor management recommendations based upon, a handful of factors: nematode density, soil type, and then genotype. I also think there should be a push towards doing these GEM trials, the genotype by environment by management experiments. The idea here is to look at a diversity of genotypes across many different environments, which would also include many different nematode situations. See how those genotypes perform, whether they're resistant, tolerant, intolerant, and then also put management practices on top of that to develop recommendations. And with that, thank you very much for your attention, and I am more than happy to answer questions live. Thank you.
Hello. Today I would like to share the research we have been conducting now for 10 years on UVC light at the Appalachian Fruit Research Station in Kearneysville, West Virginia. Today's talk will focus on a new way to use UVC light as a disease and pest management tool for berry production. We came up with a way to use UVC light without damaging plants. As we have refined this technique for disease and pest management or control, we have put more effort toward using UVC light in commercial berry production fields. And we wanted to use this to be a very user-friendly and affordable to growers. So we are working with robotic companies to develop autonomous vehicle to apply the UVC light to specialty crops like berry crops. A small amount of UV light in the sun's ray reaches the ground. That is why we get some sunburn and skin damage as we spend too much time outdoors, or if we are close to lamps that emit UV light. If you expose UV strawberry plants or blackberry plants to excessive doses of UVC radiation at one time, the leaves start to turn dark and eventually black. But if you let the plants continue to grow, then the new leaves that emerge from the leaves and the flowers that come out are not damaged. So the question is whether UVC light can be used to control diseases and pests without causing damage to plants and fruit. The simple answer is yes. Now let's look at how we managed to control diseases of berry crops. We use the combination of a short burst of UVC light at night with 4 hours of dark period following the irradiation to see if this strategy would work on fungal pathogens. We showed that this treatment was able to kill fungi that cause gray mold, fruit rot, powdery mildew, blue mold or penicillium, and anthracnose fungus. Here is an assay we ran on fruit anthracnose. We placed 50,000 CFU or colony forming units of the Calotropicum to an artificial wound on the fruit and irradiated the fruit for designated time, 30 seconds and 60 seconds. As you can see in the control fruit, the lesion covered about half an inch of the skin after 7 days of incubation. 30-second exposure reduced the lesion development significantly. Now, looking at the 60-second exposure time, you see that there is no lesion formation on these fruits. So 1 minute exposure plus a dark period completely inhibited this fungus from causing disease on the strawberry fruit. Now, next, let's look at the series of studies we did to determine the effect of UVC irradiation and dark treatment on the plant. We found that the doses we used to kill fungal pathogens at night did not have any effect on plants' ability to photosynthesize, the pollen grains collected from the flowers had a similar viability in terms of germination percentage, ability of the pollen to germinate on the stigma and grow down the style and bring about fruit set. Another benefit of UVC radiation at nighttime was that we were able to induce or increase the ability of the treated leaves to resist infection. Here we show leaflets taken from irradiated here and non-irradiated strawberry plants, and then we placed a plug of Calotropicum fungus that was growing on the petri dish, and then we placed the agar plugs on these leaflets. Notice that in the control leaves or non-irradiated leaflets, the fungus spread out rapidly from these agars placed on them and caused a tremendous amount of lesions to develop within 7 days. While in the irradiated leaves, the lesion formation did not really occur. The fungus growth was limited to the agar on which it was growing, and you see that there is no darkened area beyond where the agars were placed. This means that the fungus was prevented from growing into the leaf tissues and caused that dark lesions to develop. Next, we investigated the UVC light on several of the arthropod pests of berry crops. For the mite study, we placed 100 of these adults on each strawberry plant, and then irradiated half the plants with nighttime light treatment, while the remaining plants remain unirradiated for 1 month. After the 30-day treatments, we harvested the leaves and then counted the spider mites on these leaf samples. We found that on untreated leaflets, we counted over 150 adult mites, while on the irradiated plants, mites were counts for less than 5 per leaflet. We also did study with spotted wing Drosophila. In this study, we placed store-bought strawberries on the potted plants, and then started pulsing half the plants in the experiments, while the other half were not irradiated at all. And then once we started the irradiation treatment or pulse treatment for 24 hours, we released 20 female SWDs on each of these plants in the experiment. So the irradiation of these plants with hanging fruit lasted 24 hours, after which we removed the fruit and placed one fruit per Dixie cup and then incubated for nearly 1 month. After which we counted the number of emerged SWDs in each of these Dixie cups. We found that in control fruit, about 30% of the fruit had some emergence. The overall average of SWD per fruit in untreated or non-irradiated fruit was 12. We found just one SWD in 40 other fruit we had irradiated for 24 hours or pulse irradiated. So just one had emerged from all the fruit samples that were irradiated. So we are now looking at how we have used this knowledge to treat field-grown plants. And this involved development of robots to operate over the field during night. In 2020, we did a season-long experiment at 3 locations, one at our research station and 2 in Delaware. And the robots were built by a company called Trick Robotics that's been successfully obtained several large grants from the USDA and National Science Foundation. What we found out after 1 season-long irradiation treatment in 2020 was that UVC light irradiation at night, twice, 2 times or 3 times each week from early spring to fall, resulted in slightly higher yields and reduced spider mite and fruit rot. Let's quickly go over what is in store as far as lighting technology is concerned. Earlier, I described the 2 types of UVC radiation lamps we have used in our experiments, those 254 conventional germicidal lamps and 220 nanometer lamps that some people call them as far UV lamps. 220 nanometer or far UV lamps have been in the news for the last year or so because the scientists at Columbia University have shown that far UV lamps are highly effective in killing the COVID-19 virus. So there are now companies in US and China and Japan manufacturing these UVC or far UV lamps to be mounted or installed in airport lobbies, airplane, in trains to circulate the air in these closed environments through the UVC lamps to kill the airborne pathogens and viruses. And we have used this 220 nanometer lamp for 2 years in our laboratory. And we have find that the 220 is about 10 times more powerful than the conventional 254 nanometer lamps. So it means that the shorter exposure time is necessary to kill the plant fungal pathogens. And we have written a manuscript on this and will be submitted to a journal called Plant Protection. Other type of things that we're doing now is to look at the use of light emitting diodes in plant disease control or management. Each of these light emitting diodes are tiny, almost about a millimeter, not, millimeter to 2 millimeters in diameter, very tiny. But these little chips or diodes could be placed in an array. So you could mount dozens and dozens of these little chips on a sheet or on tape, and then use to irradiate large areas or small area or targeted areas like underneath the leaves to target particular pests and diseases. So in summary, we have developed lots of information on the use of UVC light to control diseases and insect problems. Insects that attack berry crops. And we're now in the process of developing these new robots that could be made available to growers in the near future. So we have shown that UVC light is very effective against fungal diseases, insects, and mites, and perhaps even against bacteria. And that if UVC light is used during the night, then we could use low enough doses to kill them, but not impact the strawberry plants adversely. So with that, I'll close my presentation, and maybe you could take questions.
Yes, thank you, Fumi and Inga. Very interesting talks there. So if you could both turn back on, Inga, your video and your microphone, we will go ahead and answer some of these questions that we have here. So Inga, the first question we have here, I believe, is for you. And it's, could you expand on organic methodologies appropriate for raspberries and strawberries? Inga, I'm not hearing your sound. I don't know whether anybody else is. Maybe try that. No.
Can't hear you at all. Uh-oh.
Uh-oh. Well, Inga, how are you with sign language? Or perhaps you'd like to type in your response there, maybe, and we'll see if we can get you answered that way. I don't know if you want to check some connections and see if anything could possibly be going wrong there. So, so I think what we will do is move on to you, Fumi, with the next question, which is the UV treatment sterilizing the plant surface? And I guess I've got a second part to that question, which is when you have a disease like like anthracnose that is actually existing inside of the leaves, are you then just cleaning the leaves up so that so that you don't have sporulation taking place?
Okay. Can everyone hear me?
Yes.
Okay, so UV treatment. If you irradiate or have a long exposure time, yes, it's going to sterilize, but eventually you'll end up killing the plants too. Well, with our treatment protocol, we do see tremendous reduction in the microbial populations, especially on leaf surfaces and fruit, because we had done that study 6-7 years ago. But we are not knocking everything out. There's still lots of fungi and bacteria and yeast that are living, but we're knocking them down enough that you don't get this disease to develop. We see tremendous reduction in fungi like botrytis and other fungi in the similar classification. They get knocked down by UVC light. But we're not completely sterilizing the leaf surfaces at all, because we could cover lots and lots of millions of colony units sometimes, even after irradiation.
Okay. Alrighty. So
there was another question about anthracnose.
yes.
But if you go back far enough in a nursery stage where you're actually getting the plant infected, so when you should be able to treat the plants at the nursery to prevent the initial infections to occur.
Mm-hmm. And so, yeah, so related to that, I think, some of my questions are, we're seeing some issues with like resistance, development to fungicide or to fungicides by pathogens. So could this be then a way of decreasing the number of fungicide applications needed, or be maybe a resistance management tool if we can start out with cleaner plants, perhaps in the nursery?
And then even in fruiting fields, if we treat plants with UVC light, then there is no need to minimize the use of fungicides to control subsequent infection. We could reduce the amount of fungicides to use, and then maybe mitigate the resistance development, because we're not using fungicides.
No, that'd be really, really useful. So another question, what impact does UV light have on beneficials? You already touched a little bit on the fungi, but what about things like, bees or predatory mites?
Okay, well, a good question. And a lot of people ask this, but we're using the light at night when the honeybees are back in, well, bumblebees as well. They're back in their hives, so they're not in the field pollinating flowers. So we're not really interacting with these pollinators. Okay. Now, there are other questions about, there are other beneficials like predatory mites. I think the studies that our entomologists have done or have studied from previous work done by others, that somehow the predatory mites have a way of, maybe they have a greater resistance to radiation damage, or they could move around and get away from the light source. And so they are less impacted by nighttime irradiation treatments.
Okay. That's interesting. And usually they are pretty fast moving. So perhaps that's part of the equation. So, okay.
Another question, right, about the
yeah. So does the UV light
kill SWD adults? Well, we're doing the study now, or soon to start, because we have a new postdoc on this. So we pulse the plants with these short bursts of UVC for 24-hour period. So we're not sure if it was the first flash that caused the females to fly away from the irradiated plants. And so treatment did not give them enough time to remain on the fruit to lay eggs. Or maybe they stayed on for 15, 20 more minutes and then had time to lay eggs and then fly out. But we don't know if we were causing or preventing egg laying by this flash of UVC, or UVC irradiation had any effect on the eggs that were deposited in the fruit. UVC light is not, it's not able to penetrate, more than say 1/8 of an inch or 1/16 of an inch in the fruit. And I don't know how close the eggs are deposited within the fruit. Is it less than millimeter? How long is that air tube? I don't know. I have to talk to the entomologists again, see how deep they are deposited. But I think we're somehow scattering them from the irradiated sites. So they don't have time to lay, females especially don't have time to lay eggs in this ripe fruit. But we're doing more studies this year, and then we're upgrading how we flash UVC light. Because if you flash for 24 hours, this irradiation thing is cumulative. So eventually you're going to just cause fruit to rot or just significantly soften. So we're looking at ways to using better use of those LEDs to have a short burst of irradiation, and they even use lower doses of UVC light. See, I'm sure there's an effect of just light flashing, it doesn't, probably it doesn't have to be UVC with light range, but it could be longer wavelengths, but there's this light flashing that may be causing them to scatter.
Okay. All righty. Okay. Well, I guess we'll, have to figure out what's really best for individual different issues that come up, perhaps. But that's interesting. So then, yes. So I guess this is related to that. Is do different diseases or insects require different durations of exposure for the treatment to be effective?
Well, yeah. We found out. We have done studies on six species of Calotoctron, kind of those species that make up the anthracnose, strawberry anthracnose complex. Among those 6 species, there are some that could be killed with 5-second exposure, which means there's a very low dose of UVC light, and some require 45 seconds of exposure to 254 to just knock them down. So there is a range of how vulnerable these fungi are to UVC light treatment.
Okay.
Penicillium is very easy to kill with UVC light. We have a way of killing them with just a 5-second exposure.
Okay, so post-harvest rot like that, there might be applicability there as well then with some of the post-harvest rots for
Yes,
longer
I just
storage.
talked to a pathologist this morning about that.
Okay, very interesting. And then our next question, are there any products with these light sources available for greenhouse application?
Yes, the UVC light has been used in greenhouse crops like tomatoes, cucumbers, strawberries, and lots of ornamentals in Europe, in particular in the Netherlands and Belgium, where the greenhouse production system is highly evolved, and they're using it. And interestingly, they have moved the UVC treatment time from daytime to nighttime based on our results that we published 6 years ago. So nighttime seems to work better because we could use much lower doses of UVC light to control these fungal pathogens and even 2-spotted mites. So there are commercial greenhouse operators using this UVC light technology.
Okay, all righty. Well, that definitely helps with answering that. I guess, related to coming back to the one question for Inga on the organic methodologies. I know there, is some interest in this ASD, the anaerobic soil disinfestation for nematode control, and that might be one option that might need to look into more related to that. I don't really have any more information than that, and we did kind of lose Inga here, it appears. So so that might be a good question for an extension article sometime, though. So so I think with that we are at our time, and it looks like we've answered our questions here. So I'd like to thank both Fumi and Inga for these talks. And from here then, I guess we're going to wrap things up. And so I'd also like to thank the attendees for the interaction, and give everyone a final reminder to check out the sponsor and exhibitor information, as we really appreciate their support. And with that, I would like to thank everyone, and I hope you all enjoy the rest of the conference.